A clever person solves a problem, a wise person avoids it. Albert Einstein. Albert Einstein was a very smart physicist. Because of his love for physics, I'm sure he would have loved Valorant. In this video, we'll discuss topic number 3. Shoot down the drone. This topic requires a basic understanding of physics, so let's start with that. In physics, a projectile's motion is split up into vertical and horizontal motion. These two motions are independent of each other, one motion not affecting the other. For example, an apple dropped from a table and an apple pushed off the table will still touch the ground at the same time, even if the apple was given force horizontally. The two motions can be expressed in these two equations, where x is equal to v subscript of 0 subscript of x times t, which is time, and y equal to v subscript of 0 subscript of y times t, minus 1 half times g, being gravity, times t squared. In the equations above, the x of 0 and y of 0 stand for the initial position of the projectile, and v of 0 subscript of x and v of 0 subscript of y stand for the initial velocity, while the subscripts x and y stand for the initial angle of launch. T is the time elapsed since the initial launch, and g stands for the acceleration of gravity, which is negative 9.8 meters per second squared. Now that we have a basic understanding of the physics required, let's move on to the topic.
The first question asks, find the formula for the x and y coordinates of a projectile with no friction launched from a cannon as a function of time, given that you know the muzzle velocity, v sub 0, and the launch angle, theta. Assume that your cannon is at height 0 on the ground, and that t equals 0 corresponds to when you fired the cannon. The first two equations shown can be used to express the coordinates of the projectile, but you can further simplify the two equations into one equation. This one equation can be used to graph the trajectory being the path a projectile will take. We can first start to combine the two equations by solving for t, the time variable. Solving for t in the x equation gives us this equation. The amount of time elapsed since the launch of the projectile is x divided by the initial velocity multiplied by the cosine of the initial angle. Now we can substitute this value with t for the y motion equation. Simplifying the equation gives us this equation. This equation is used to graph the trajectory of the projectile, giving us the answers to the first question.
Before tackling the second question, the topic gives a little information about the problem. Imagine that you are playing some sort of video game in which you are trying to protect a base from enemy drones. The drones carry explosives that will damage the base unless you successfully shoot them out of the sky. They are flying in a straight line path towards your base as shown in the diagram, and furthermore, it is determined to be flying at a speed of 50 meters per second. There are two bits of information that are most important here. The drone is 5,000 feet away horizontally and 2,000 feet away vertically, and that the drone is flying towards the base at 50 meters per second. We can easily graph this. The base is on the origin, and the drone is at the coordinates of 5,000, 2,000. Moving on to the second question, it asks, determine the angle at which the enemy drone is approaching the base. Solving for the angle just requires the use of the trigonometric ratio tangent. The tangent of the angle is equal to the opposite side divided by the adjacent side. In this case, it is 5,000 over 2,000, which is just 5 over 2, or 5 divided by 2. Now we just have to find the arctan of 5 over 2. Plug that into the calculator and you've got approximately 68.199 degrees. With that, 68.199 degrees is the angle at which the enemy drone is approaching the base.
The topic gives us a little more information before the third question. The base's cannon has a muzzle velocity of 150 meters per second, and you can shoot it at any angle you want. You know you must hit the drone when it's at least 1,000 meters away from the base in order to avoid damage. Now we know we must shoot the drone before it reaches a zone of 1,000 meters, and that the cannon launches the cannonball at an initial velocity of 150 meters per second. Moving on to the third question. Suppose the launch angle is set at 45 degrees. Determine the time at which you must fire the cannon in order to hit the drone. Finding out when to launch the cannon first requires finding the intersection of the cannonball's path and the drone's path. The drone follows the equation y equals 2/5 x because it goes in a straight line towards the origin, which is the base. Setting the two equations together and solving for x returns the x-coordinate at which they intersect. This gives us the x-coordinate of 1376.15. Plugging this x-coordinate into the trajectory equation returns 550.46. The point of intersection is 1376.15 and 550.46.
Then, we'll need the distance between the base and the point of intersection. This can be found using the Pythagorean theorem to solve for the hypotenuse. This ends up being 1,480 to 0.16 meters. The distance from the drone to the base is also required. This distance from the drone to the base is 5,385.16 meters. Subtracting these two distances gives the distance from the drone to the point of intersection. 5,385.16 minus 1,480 to 0.16 is around 3,903 meters, taking into account the drone's speed 50 meters per second. It takes the drone 78 seconds to reach the point of intersection. Plugging the x-coordinate of the point of intersection into the horizontal motion equation gives us the time it takes for the cannonball to travel to the point of intersection. Solving for t, it takes around 13 seconds for the cannonball to reach that point. Finally, subtracting these two times gives us the amount of seconds we wait to fire the cannon, 65 seconds.
The final question asks us to determine the minimum launch angle that will hit the drone a safe distance away from the base. Thankfully, it tells us not to worry about the timing. We can recruit the help of a handy digital tool, Desmos. Using Desmos, we can find the minimum angle where we can hit the drone without damaging the base. The functions seen on screen right now make up the graph. The first function represents the trajectory of the cannonball. The second function, in blue, graphs the drone's path. The third function shows the danger zone in which the drone is too close to the base and cannot be shot. It is a straight line that extends out from the base towards the drone at a distance of 1,000 meters. The slider for the variable A controls the angle at which the cannon shoots the cannonball. Through extensive adjusting of the A variable, we can find the minimum angle at which the cannonball hits the point of the black equation. The point at which the minimum launch angle is for hitting the drone within a safe distance. The minimum launch angle at which the cannonball will hit the projectile outside the danger zone is around 35.0771 degrees.